Okay, so we have been analyzing circuits and we've been using pretty straightforward, simple circuits where we've been able to take perhaps resistors that are in a line and bring them down to an equivalent resistors, or maybe we had resistors in parallel and brought them to an equivalent resistance, or even a circuit that has both things in series and parallel that we've been able to break down into an equivalent circuit with a single voltage source and a single resistor. This then allowed us to determine what the current was within that circuit, and then we backtrack to look at the current maybe in the individual branches. Well, today we're going to look at what happens when we can't get down to a simple circuit with only a voltage source and a resistor. What happens if we have a circuit like this? One where there are branches, there's multiple voltage sources, and this is as simple as it gets. What do we do in a situation where I can't get down to a single voltage source and a single resistor? That's what we're going to look at today. And we're going to identify two rules that are going to help us to analyze this circuit or any circuit where in its simplest form I have multiple branches. Those rules that we're going to look at are known as Kirchoff's rules or Kirchoff's laws. And there are two of them that are super powerful as we continue to analyze circuits and learn how to get the currents out of the individual branches within this circuit. All right. The first rule that we're going to learn about is what's known as the junction rule. The junction rule is straightforward as it pertains to conservation. It tells us that the current going into a junction has to equal the current coming out of a junction. That's not too hard of a stretch because where else is it going to go? So let's first define again what a junction is. So if I have a wire that suddenly has two wires moving off from it, this location is what we call that junction. The junction rule simply tells us that if I have a current coming into the junction, we'll call that current 1, that it has to equal the current going out of the junction. So if I write that into a mathematical equation, I see that current 1 has to equal the current in, the sum of currents 2 and current 3, the current going out. Now, you notice that I made a choice at what directions those currents were going, and that we get to do. We get to choose as we analyze the problem. It's the first step in our process. We choose the direction of the currents in the branch. Now you might be thinking, well, what if I choose the wrong direction? What if the current actually isn't traveling in that direction in a branch? That might happen. Turns out as we analyze the problem, however, the physics will tell us. If we choose incorrectly, if, for example, this is the correct way the currents flow, but instead maybe I chose in my analysis that current 1 and current 3 go into the junction, and current 2 goes out. Now if I write my junction rule, well, what's in I1 plus I3 equals what goes out, I2. Those are different equations. However, the physics will tell me if one of these is incorrect. Because if I3 really does go out and I've drawn it going in, when I solve for I3, it's going to be negative. And if it's negative, that tells me, oh, you made a mistake. The current's in the wrong direction. So when you complete the analysis, you know it should be going in the other direction. If it's positive, I didn't make a mistake. So when we know whether or not we made good choices at the end of the problem, when we analyze the currents and we find out whether they're positive or negative. Now that comes with one small exception, and that exception is you can't have everything going in or everything going out. So real quick, what would that look like? Well, if I said, all right, well, I1 goes this direction, and I3 goes this direction, and I2 goes this direction. Well, everything's going into the current, into the junction, and nothing's going out. So we can't even write a junction rule equation for that. So we know something's wrong there. All right, so given these two options were good, it'll tell us as long as we don't make this fatal flaw of everything going in. Okay, so that's our junction rule. And the first step in analyzing currents in a circuit is to define the directions of the current, thinking a bit about that rule, and then we can write the equations that work at the junctions. So let's take our circuit, and I'm going to say maybe current 1 heads in this direction. So in this direction is current 1. I get to a junction and it splits. I'll say that current 2 goes along this branch, and I'll say current 3 goes along this branch. All right. Once I hit this junction, 2 and 3 come back together and they lead back into current 1. So now that I've identified all of the currents in every part of the circuit, I can write my equation for that junction rule. I will look at first, what junction am I looking at? Well, let's look at that junction. What are the currents coming into this junction? Well, I have current 3 coming in, and I have current 2 coming in. So current 2 comes around and goes into that junction. What's going out of that junction? Well, it's current 1. So current 2 and 3 come, oops, that's a 3. Current 2 and 3 come into the junction, current 1 goes out. So I've used my junction rule for that junction. There's another junction in this problem, and you'll find if I use my junction rule there, I actually get an equivalent equation. That tells me that I have one equation that tells me current 1 is equal to 2 plus 3, but I can't solve for 1, 2, or 3 because that's all the information I have. If I have 3 unknowns that I want to solve for, I need 3 equations at least that have those same unknowns. And so we are going to look to the second rule to provide us that information. The second rule is called the loop rule. Now the loop rule I think is the funnest rule because it generates these glorious equations. It tells us that the sum of the voltages along a loop that I get to draw are equal to 0. So what's a loop? A loop is when we start at one spot in our circuit. I'm going to start right here. I'm going to call that spot A. And I put my pen down and I draw a big circle that never have to lift my pen up. That makes a circle back to A. So let's look at what those circles look like. Well, I could start at A and I could go around the outside and back to A. There's a loop. I could also start at A and I could go along the inside back to A. There's another loop. And it turns out there's one more loop in this circuit. It doesn't start at A, but I could maybe start at this corner and I can go around that loop. So in this circuit, I have 3 loops. For every one of those loops, the voltages along those loops are equal to 0. I have 3 more equations that I can sum the voltages along that loop to equal 0. That might give me a shot at solving for these currents. So let's look at how this loop rule applies mathematically. All right, we're going to start with this first loop. So the sum of the voltages along loop A1, the big one. All right, so what is the first thing I encounter as I move along this loop? I encounter a resistor. We know that voltages can either go up across a resistor or down across a resistor depending on whether or not I'm traveling with my current or against my current. We learned that earlier. And so in this case, am I going with or against the current? Well, we have to look at what current's going through resistor 4, and we see that it's I2. So I2 is the one that's going to be going in across resistor 4. I1 is going in this direction. I1 goes across resistor 4 in the same direction as my loop. If the current is in the same direction as the loop, then the voltage across that resistor drops. All right, as current travels through a resistor, the voltage drops. We learned that before. So that means that the voltage drops across resistor 4. We give it a negative. Now I'm going to hit my voltage source. I'm going from low side of the voltage to the high side of the voltage in the direction of the loop. I'm going from low to high. If the loop goes from low to high across a voltage source, the voltage across that source is positive. I'm going from a lower voltage to a higher voltage. I'm adding voltage as I move along that loop. So that's voltage 1. It's a positive. The next thing I run into in this big loop is resistor 1. Current 1 is going through resistor 1, and it's in the same direction as my loop. So I get a voltage drop across resistor 1. I then encounter resistor 2, and my current through resistor 2 is current 2. It's going in the same direction as my loop, and I get a drop across resistor 2. The next thing I encounter is voltage 2. I'm going from high to low, a higher potential to a lower potential. That's a drop in the voltage. So if the loop goes from high to low, then my voltage drops. So voltage 2 is going to decrease the voltage through that loop. These are the two loop rules that relate to voltage sources. So I have an equation that tells me that the sum of these voltage across these elements have to equal 0. How are they related to the current? Because that's what I was going to solve, right? I was going to use these rules to solve for current. Well, that's Ohm's law. So we know that the loop is equal to 0, and we're going to apply Ohm's law. The voltage across resistor 4 is just the current through resistor 4 times its resistance. Resistor 4 has current I1, so minus I1 R4. Then I have my voltage source 1, which is known. Resistance 1 is current 1, so that's minus the current through resistor 1 times R1. Resistor 2 is current 2 through resistor 2 minus V2. So now I have another equation that has current 1 and current 2 in it. I'm getting closer to my ability to solve for the currents. I don't have current 3. I need another equation that has current 3 in it to actually solve for it. So let's find a loop. Let's use the loop rule again to find a loop that has current 3 in it. Well, either one of my two loops have current 3 in them, because this loop's going to go through with current 3 at some point, and this loop's going to go with current 3. So let's use loop A again. So the voltage is across loop A, and this will be A2, so this inner loop here. So we start at point A. Some of these voltages all have to equal 0. As I travel along this loop, the first thing I encounter is resistor 3. As I move in the direction of this loop, am I moving with the current or against the current? Well, I've drawn current 3 in the downward direction. I'm moving in the upward direction, so I'm going against the current. If the current is opposite the loop, then the voltage increases across that resistor, so it's positive. So the voltage across resistor 3 is positive based on the direction I made my loop. The next thing I encounter is resistor 2. So I have the voltage across resistor 2, and I'm going with the current. It's negative. The next thing I encounter is the voltage source as I go through my loop. I am going from high to low, so my voltage source goes from high to low. It's a voltage drop. And now I'm back to my starting point, so I know this equals 0. I once again can then use Ohm's law to get currents into my equation so that I can solve for currents, and I find that 0 is equal to, well, what current goes through resistor 3? Current 3. So I have current 3 times R3 minus the current through resistor 2 times the resistance of resistor 2, using Ohm's law again, minus my voltage source 2. So now I have another equation that I can use to solve for my currents, and now I have enough. Now it just takes math, a little algebraic manipulation to solve for my 3 currents. But just for the sake of practice, let's do that final loop, this loop here, just to practice. We're going to call that the voltage through loop B. All right, so we'll say this is point B. If I start at point B and I go in this direction, the first thing I encounter is resistor 1. My current is in the same direction as my loop, so I know that the voltage across resistor 1 is a drop. I then encounter resistor 2. My current is in the same direction as my loop. Sorry, resistor 3. So the voltage across resistor 3 is a drop, another negative. I then encounter resistor 4. Again, the current through that resistor is in the same direction as my loop. So I get a voltage drop for resistor 4. And then I hit my voltage source. I'm going from low to high. Low to high gives me a positive voltage increase. Using Ohm's law, I can simplify this, or I can add in the currents for this, and I have minus I1 R1 minus I3 R3, the currents through resistors 1 and 3. The current through resistor 4 is I1 plus my voltage source 2. And I have another equation. It's not necessary because I had 3, but just to close that loop. Ha ha ha. All right, so 2 rules that we can use, the junction rule and the loop rule. Remembering to set that junction properly. Not worrying so much about whether you're in the right direction. The physics will tell us. And then we can solve any complex circuit. We just have to define those junctions and those loops. Good job.